Okay, this is going to be a tutorial going over solving a basic two-dimensional diffusion problem with Palabos. And so we'll be using this LBM library, and so that's what I mainly want to go over in this video. And so if you need the Palabos codebase, you can go to the University of Geneva Palabos website. And so Palabos stands for Parallel Lattice Boltzmann Solver. And so from here you can click on their GitLab repository, and you can click this link right here to clone this repo. And so the syntax is just git clone and then that URL, and that will download the code base. And so now you have the Palabos code base. And so you're ready to go. And so if you're planning to use this, I would put this repository somewhere where, for instance, that it won't just get deleted. Sometimes if you just leave a bunch of stuff in downloads, it gets lost, or put it in temp, or it'll get lost. So I would recommend to put it somewhere where it'll be kind of safe. So Palabos, to be clear, is a code base, so it's not you use this to compile your program. So it doesn't, for instance, need to be in like USR bin or something. But that's just something to think about. And so now this problem that we're going to solve is from this book by Sukop and Thorne. This Lattice Boltzmann Modeling Introduction for Geoscientists and Engineers. And so Chapter 8 of this book goes over solute transport. And so the problem that we're going to solve, again, we're solving the diffusion equation. And let me find again where we were. This equation 129 is the solution to the diffusion equation that we're going to analyze. And so if I don't want to go over the actual math of solving the diffusion equation, if you're interested in that, this book, The Mathematics of Diffusion by Crank, Chapter 3, he goes over the infinite and semi-infinite media. And so here, 3.2, this is the two-dimensional diffusion equation. And so equation 3.4, so within the first page of this chapter, he's already shown you how to derive this solution. And so this equation 3.4 is this same equation right here, except with the initial concentration term. And so what this equation is saying is the concentration as a function of radius is the initial concentration plus this initial mass divided by 4 times pi times the diffusivity times time times exponential of minus radius squared over 4 times diffusivity times time. And so again, that's this same equation that they have right here. And so what we want to do is to essentially recreate this figure 69 from the Sukop book, where they're comparing the LBM with this analytic solution as a function of time. And so this is formulated for an infinite domain, this solution that Crank derived. And so I'll show you, we're not going, obviously we can't simulate infinite space. So we're going to use this truncated space, and we'll cheat by not allowing the mass to reach the boundaries before our final time step. So this is effectively our situation that we're going to model. And so we have 1,000 lattice units in the x direction, 1,000 in the y direction. And our initial mass is going to be 1,000. And so this is showing kind of how this is oriented as like just a square domain, and this is at 500 and 500. And so our diffusivity we'll use is just going to be 1/6, and the relaxation time tau for the LBM is defined as 3 times the diffusivity plus 1/2. So this is basically going to be the setup for the LBM that we're going to use. So now we'll get into the code. And so real quickly, I'm a big fan of Vim, and but I don't use Vim normally when I'm using Palabos, and I'm sure if people out there are going to probably tell me that I'm just need to suck it up and learn to use C tags correctly, but I find that VS Code's ability to query code bases to be a little bit easier to use than C tags in pure Vim, because normally when I'm using Python or doing scripting, shell scripting, I'll just use a Vim and a terminal, but this is normally how I like to have my workflow for Palabos. So I've still got obviously a terminal here, but this cpp properties.json file has the path to the Palabos source and these external libraries, so that when you're in a text file with the Palabos program, it knows where all these classes and functions are defined, so that you can use the keystroke control and square bracket to jump to where these are defined. And so that's important for when you're learning Palabos, especially if you want to learn how to extend Palabos, that you learn how they've written their code, because you need to essentially implement their inheritance scheme similarly to how they've done their stuff. So that's just sort of an aside, but anyway, you can obviously do this with just Vim or any text editor. You don't have to use it, but this is how I like to do this. So first, we're just implementing or importing rather these Palabos 2D header files, and so that gives us access to the Palabos namespace and to these descriptors and this, for instance, this class and these functions. And so, like what I was saying with this control and right square bracket, if you wanted to see where the D2Q5 descriptor is defined, you can just put the cursor on this and hit control square bracket. And so you can see right here, this is the path that it found where this file is defined, advection diffusion lattices.h. And so we can just go down the rabbit hole. And so now you can see here are the parameters. And so typically in the syntax for describing lattices in the LBM is D and then followed by the number of directions, or dimensions. It can be 1, 2, or 3, and then the number of directions. And so this is the D2Q5 lattice. It could be D2Q9 is another option for a 2-dimensional lattice. And so what I've shown over here is this is the directional scheme for the D2Q5 lattice in Palabos. And so if you wanted to see how they've defined that, you can see, okay, this is where the lattice directions are. So again, control and then right square bracket. So it brings you down here, and so this is an array, and so you can see 0, 0. The first element of this array is 0. The first element from zero-based indexing is -1 in the x direction 0, so that's this. 0 minus 1 is 2, 1, 0 is 3, and 0, 1 is 4. So that's why I've shown this right here. This is how Palabos has defined their D2Q5. And you can do the same thing for their D2Q9. You can go down their essentially through their code base and see how they've defined these other lattices. And so when you're using that control right square bracket, if you press control T, it'll go backwards. It'll scroll backwards through the history that you've gone down. So you can go back up to, pressing that a few times brings you back up to the main file. So we're back now at our diffusion D2Q5 program. So that was just to show you why that is really, really convenient for surfing through a code base. So the descriptor gives the all those parameters that I was just showing you. So that tells Palabos, for instance, what this arrangement is and what the weights are for the different directions. And so if, for instance, you wanted to define your own descriptor, you can easily just look at how they've done this and implement your own version. And so the dynamics we're going to use are the BGK dynamics. And so you could do obviously the same thing. I'm not going to belabor that, but just go down and see how this is all defined. And so I'm going to come back to this function, and I'm going to go over the main program first, and then I'll come back to this when it gets called. So, as I mentioned, the simulation we're doing, we have 1,000 points in the x direction, 1,000 in the y. And so I'm using plint instead of a regular integer. This needs to be an integer, not a float or a double. And so plint is just the Palabos implementation, essentially, of an integer. So it's nothing really special, but I'm just using that. And so the diffusion coefficient is 1/6, as I mentioned. And the maximum number of iterations we're going to do is 1,000. So again, if you take the maximum iterations too far, this mass will diffuse beyond the edges of the boundaries, and the assumptions for the analytic solution are not satisfied if the domain can't be considered infinite. So you can't take this to an infinitely high value for the case that we're doing, but that's just something to think about. And so the relaxation time, again, 3 times the diffusion coefficient plus 1/2. This is the relaxation frequency, and this is our initial point source mass. And so this call right here is instantiating the lattice. And so this multi-block lattice 2D is a kind of a catch-all class from Palabos. It's more complex than a 2-dimensional array. You can read about it in the Palabos user guide. Its template calls for a type def and a descriptor. So, if you're wanting to solve the Navier-Stokes equation, you would have a different descriptor than this, but this call would be essentially the same. You wouldn't have this advection descriptor, but the way that you instantiate it with, you call it, I'm calling this add lattice for advection lattice, and then it needs the nx or number of lattice points in the x direction and the y direction, and it needs a dynamics argument. And so that's where you're passing the relaxation frequency to your lattice. So this is, again, a very nice abstraction made by Palabos. And so then we're establishing periodicity on this lattice. And so essentially all that means is we're saying this point is adjacent to this point, and this is adjacent to this. Again, it doesn't really matter because within our time frame, the mass is not actually traveling beyond these edges, but I'm just leaving that periodicity like this. So that's how that is defined. And so this is now going to call the center point setup. And so this is establishing our initial condition. So this is a void function, so that means this function doesn't return anything. It's operating on our advection lattice on a pass by reference. So calling this ampersand, that means that we're passing a pointer to the add lattice as an argument, and then the initial, the point source mass is the other argument to this function. So it's using this getInX method and getInY method from add Lattice. Again, I'm just using this plint class. And so the center X is half of that and center Y is half of the NY. And so box2D is a struct from Palabos that you can use to essentially highlight two-dimensional sections of the domain. And so this is actually just selecting a point. And so it takes, you can think of it as x0, x1, y0, y1. And so center x, so x0 and x1 are the same, and y0 and y1 are the same. So this is just selecting a single point. And then our cinit is 0. So that's going to be the value assigned to every point except for this central square. So this array 2D is the velocity array, which is obviously 0. And so this call to initialize at equilibrium, it takes its argument as add lattice, and then I'm giving it add lattice bounding box. This method just returns a box2D instance that encompasses the whole lattice. And then I'm saying the initial concentration is 0 and the velocity is 0. So this instantiates the initial concentration to be 0 everywhere. And this instantiates the concentration to be M0 at the center point. So I'm just using two different calls to instantiate these initial conditions, and then add lattice.initialize. This makes it ready to stream and collide. So that's what center point setup does. And so now we're getting to PLB-OF stream. And so this is what I'm going to use to the output the concentrations along a single line. And so that's what I've shown here is we're going to extract the concentration along this line to compare it with this here. And so this for loop is the time stepping. And so we're using IT as the iterator. And so this is just standard C++ for loop syntax. And so we're saying if iterator mod 50 equals 0, so every 50 iterations, write this to the console and write to successive profiles this compute density function. So this takes add lattice as an argument and is extracting box2D. It's doing what I had just shown you. It's extracting this line right here. So it's going 0 to nx, and then it's taking ny over 2 to ny over 2. So that's exactly what this is showing right here. And then add lattice.collide and stream. This actually, this operation does the obviously colliding and streaming and moves the mass from the center and diffuses it outward. So this is overall not a super complex program. Again, I wanted this to be like maybe the most simple Palabos program possible. And so now I'll show you the makefile. So this is their older makefile. So I downloaded Palabos several years ago. They use CMake now, so they have a new build system, but their new build system will still work with this. But the thing you need to be careful of is where Palabos root is. So you need to know where source and external libraries are with respect to where you're compiling, so that it knows where those libraries are. And so obviously if you have the MPI compilers, or if you're trying to run this on a cluster, you would want to make this Boolean to be true. But it can obviously be false, and you can run it on a single core if you want. Um, so I again, I've already compiled it. And so if you want to run it in parallel, this is what the syntax will look like. Be like that, or npr run, whatever your preferences for that. But I'm just going to run it on a single core. And so this is it. It's running now. And again, it's just printing that, writing concentration profiles. And it's writing this file right here. So this file already existed, but it's just overriding it. And so that's this concentration profiles.dat. And so if we want to see, this file is just a gigantic, and you can see over here, it's just many lines of numbers, and that's what we wanted. But so I wrote this other little Python script to parse this and to plot it so we can view the data like this. So we can look at that now. So real quickly, just going over what this does. This just reads that text file that I wrote, that the C++ program wrote, and converts it to a MP array. This is just a color cycler. And so the main program, I just hard coded these in X and Y values, diffusion coefficient, M0 obviously. And so this line right here is solving the analytical expression. And so again, it's just solving this M0 divided by a 4 pi dt exponent minus radius squared divided by a 4 dt. And so it's plotting that, and then it's plotting the LBM solution. And so it's offset. The LBM solution is offset because when you look at how this is defined, it goes up to but not including 1000. So by instantiating the center of our center point setup to be at 500, it's off by 1. So this just aligns the LBM solution with the analytic solution, but it's it's just a trivial offset. And so now we can look at it. And so this script is just called figure 69. And so you can see the dots are similarly to figure 69. The dots are the LBM solution, and the solid lines, or these are dashed lines, are the analytic solution. So we can see that it is tracking through time this behavior. And so if you zoom in close, you can see that it's obviously has some numerical inaccuracy that is accumulating. But if you're interested in making it, or refining it rather, you could for instance use a different lattice. You could use D2Q5, or finite volume. You could use a different numerical scheme. This is just to show you though how to essentially capture this physics with Palabos. And so I have this argument to main that is just essentially controlling the density of that plot. So if you wanted to see less of those lines, you can change that and run this again, and it'll now do every other line, so it's less dense. And again, you can zoom in and see if it's working correctly. And so I have a little README in here. And so I have a link to Mathematics of Diffusion if you're interested in looking up the actual derivation of the analytical solution. You can look at that. And so it's also just got the the little figure, and this GitHub repo will have this little Python script and obviously this, but you'll still need to download Palabos if you want to run or compile this program on your own computer. I didn't put the actual binary on there. So yeah, I think that should be hopefully a good intro tutorial to Palabos.